Okay, so this is going to be looking into sort of the theoretical kind of background of iterative image reconstruction. I'll be covering least squares, maximum likelihood, and also regularization. So this is the basic situation where we have some measured data. So for example, this could be a PET sinogram, or it could be case-based data, or it could be some CT data here. And the goal in iterative image reconstruction is to find an image X that best explains that measured data. So here I'm showing an FDG PET image associated with that sinogram, for example, MR, T1 weighted MR associated with case-based data, and then forgive the simulation data here for CT, just showing the link between a CT basic phantom and the measured data. And the link, of course, as we know, between the image X and the measured data M is the system model. And the system model is unique for each modality. It'll be a particular choice for PET. We can go into that into more detail as required. I'm sure you know a lot already. For MR, it's typically a discrete Fourier transform with undersampling, and obviously you've got your coil sensitivities before then as well. And then typically some kind of line integral model, radon transform, cone beam, and so on for CT. And all of those are captured in this simple linear model that I'll be assuming throughout, which is that you've got a vector X, which is the object representation or the image, related by a system matrix A to the measured data. So I'm just going to show an example there whereby this is showing one element. I'm going to be using AX and then subscript I to denote one element in the measured data. And that's going to be related through the system model, this matrix multiplied by a vector. And the matrix is effectively showing us the elements in the image or the object representation that are associated with a particular measurement. So I won't go into more detail about the system modeling. Hopefully you're already familiar with that, and I'll be assuming that throughout now. But I will just go into a little bit more quick detail on the object representation. This is effectively what we're doing in medical imaging is that we're imaging a continuous object. So I'm trying to represent that here as a simulated PET distribution. This would be a continuous function, if you like. And what we're doing explicitly with iterative reconstruction is discretizing that continuous distribution into a discrete form like this. And I've shown a very extreme discretization on the right-hand side here, just to really illustrate the point here. I've just got 8 by 8 pixels. And the point being that we just stack those values into a tall column vector. So if it's just an 8 by 8 image, then we have a 64 element vector X. And so image reconstruction, iterative reconstruction, is all about finding X, which is a representation of that continuous object. And so to be explicit about that, that's the continuous object, whether it's a radio tracer distribution, or if it's a MR net transverse magnetization, or a mu map for CT. We're saying it's approximately equal to a set of basis functions, and I'll be assuming pixels or voxels throughout this presentation. And then we've got coefficients, which are the elements in that vector X. So there we are, just spelling that out. Object representation parameters. So image reconstruction, as I've said in the past, should really be called estimation of object representation parameters. That's what we're really doing here. And then just to spell out the example there, I'm just showing 3 pixels and showing that, of course, these representations could just be regarded as these top hat pixel or voxel basis functions with particular amplitudes given by those coefficients which are stacked in that vector. So that's just to really make it clear what we're talking about in terms of what we're estimating, especially when it comes to statistical iterative image reconstruction. So basically pixel or voxel values. Okay, so first of all, I'll say what we can't do, okay? So this is based on mathematical issues, if you like. We can't claim that the measured data, whether it's a PET sinogram, whether it's case-based for MR, whatever, we can't say that that's directly equal to object representation, which I'll be calling image from now on just for convenience, because we all call it image. We can't say that that measured data equals the system model times our reconstructed image, okay, for a number of reasons. First of all, typically the measured data are noisy, and so this vector on the left-hand side of measured data won't even be consistent with our system model, so we can't expect this to hold. And then, of course, our model is exactly that. It's a model, and it's going to be imperfect. And furthermore, it's really presumptuous to even assume that we could even do this, because the chances are that the matrix A won't even be square. We'll be dealing with either an underdetermined, when we've got missing data, or an overdetermined with 3D PET system of equations, and in which case the matrix A isn't even square. So this kind of expression here, A minus 1 doesn't even exist. So just to first of all clear out what we can't do mathematically. If we intuitively tried to remedy that non-square matrix, then intuitively what we could say is, well, let's just do the adjoint of the system model. Let's just do the transpose of it, or the conjugate transpose for MR. And that corresponds to the so-called back projection operation. So this will be some measured data. We could back project it using A transpose or A star, the adjoint of the system model. And then we do that to both sides of the equation. And then what we've got here now is a square matrix. And so we could rearrange that as shown to arrive at an attempted solution here, which, as I'll show you presently, is actually the least squares solution. But here I'm just motivating it intuitively, saying we could come up with some image reconstruction X, which is just equal to the inverse of this square matrix A transpose A, operating on the back projection of the measured data. But again, to make the point, that matrix A in real reconstruction, especially for PET, for example, which is what I know very well, the matrix A is colossal. I won't even go into the calculations. And 3D reconstruction by direct least squares inversion isn't even practical. Obviously, what we'd want to do is something like a singular value decomposition and then some kind of pseudo inverse, whatever your favorite method is. But we can't do it because the matrix A is so big. And also, of course, as this is a least squares solution, and I'll be showing in a moment, that's implicitly assuming Gaussian noise, which for PET isn't even the correct noise model. It's Poisson distributed noise. Okay, so those two are also non-starters. And so these two slides, part one and part two of issues, are really saying, well, that's the context. So why is it that we need to even do iterative reconstruction? Well, hopefully I've already begun to motivate it through these issues. So what can we do then? Well, sorry, just to repeat what we can't do. We know we can't say M equals AX, and therefore we're saying M minus AX equals 0. Can't attain that. M is noisy, not even consistent with the forward model A. So what is it that we could do? Well, let's, instead of trying to find an X that solves that, which won't work, instead let's find an X, which when we forward project it with the system model A, is giving some small residual vector, which I'm going to call delta here. Instead of 0, we're saying, well, no, okay, it's going to be wrong a bit. And so let's admit it's wrong. And then the goal of our reconstruction will be, well, let's try and minimize the size of that residual. So find the image reconstruction X, which delivers the smallest possible delta. And to measure the size of that vector, we could naively just sum all the elements as shown there. But of course, positive and negatives would cancel. And so intuitively, we'd say, well, okay, let's take the absolute value and square them. So this corresponds to the L2 norm of that delta vector. And this, of course, is therefore leading us to the least squares definition. This is the least squares objective function, where we're saying find an image X, which when you forward model it, matches the measured data M as best as possible, knowing it won't be 0, but instead we just want to minimize that distance, that discrepancy. And this is the least squares objective function. And in order to achieve this, we talk about an algorithm, so this is the argument X here, which when put through A will minimize this overall least squares objective, okay? And so I'm going to use a hat here to say that this is the X that delivers the minimum of that least squares objective function. So we've got objective and we've got many possible algorithms that could deliver this minimum. Okay, so this also relates to statistical image reconstruction. So just to show you the example for MR here, which uses a Gaussian noise model, I'm just going to show that the Gaussian noise model leads us naturally to a least squares solution. So what we're doing here is saying find an image X, so there's X, run it through the system model A, like we've seen before, in order to match the measured data M. So this is now case-based data for MR, of course. And so there I'm showing X, running it through the system model A, which of course, remember for MR, that's going to be call sensitivity Fourier transform, and then undersampling to strip out the k-space values you haven't measured. And what we're saying here is, well, okay, that's going to predict, if you like, model the mean k-space. And we can look at one particular element, I've exaggerated it here, in k-space, and we need that model, AX, in fact, we subscript I, to match the measured data. Okay, and so this is effectively a Gaussian model where we're saying that the mean of the Gaussian is AX and the noisy measured value is M. Obviously, I'm dealing with single elements, subscript I, and this is just the definition of the Gaussian probability distribution, which I hope you're all familiar with. And with the likelihood, what we're talking about is what is the likelihood of an image X given the fixed measured data M. So find the X that maximizes this probability. And the likelihood is saying, well, okay, let's consider the product of all of those probabilities, assuming independent measurements, find the X that delivers the maximum of the product of all of those probabilities. So hopefully that's a fairly clear concept, because obviously if you want to maximize each and every one of them, then if you maximize the product of all of them, that will do the job of maximizing each and every one of them individually. Okay, so this is where we get now the concept of where I'm heading, which is least squares, because this is a rather ugly thing to try and maximize. So what we do is we take the logarithm of it to get rid of that exponential. So we take the natural logarithm of this Gaussian likelihood. The product now goes to a summation and the exponential disappears. And then what I've done is just show, of course, where we're headed, which is the least squares here. And then I've just taken this out as a constant, assuming constant variance in that Gaussian. And then you can see straight away that if we're finding an X that's going to maximize that Gaussian log likelihood, then that will correspond, if we pick sigma is equal to sigma squared equal to 1, then it's going to correspond to minimizing the negative log likelihood. So if you take the negative of that, and now we just change the maximization problem to a minimization problem. And so hopefully you can see that maximizing that corresponds to minimizing the negative log likelihood. So this least squares objective function we can see relates directly to a Gaussian noise model. So where we were before was saying, well, okay, we know we can solve this. And in fact, you can do it properly analytically. You just differentiate this with respect to a single pixel value xj, set that derivative equal to 0 to find the minimum of that objective function, and rearrange. And then what you get is none other than what we've already looked at before. It takes a couple of minutes to show you the derivation. It's pretty simple, but you end up with exactly what we saw. But just to go back to where we were, which is to say that that's not practical to do, and that's why we're going to need iterative reconstruction. So that's the motivation on this next slide, which is we need, therefore, to find the X that minimizes that least squares objective without, this is a key point, without needing the whole system matrix to be stored in memory. So when you're doing kind of forward models, system models in software, often these are done via calculations on demand. You certainly don't store the entirety of that acquisition model in memory because it's just be colossal. So this is the least squares objective function I'm showing in blue here. And what we're going to do is make the following observation. Well, if we had some guess, so I'm going to call that X superscript K to denote some guess of the reconstructed image. It could be 0 valued if we're doing the least squares algorithm, or uniform valued. Given some guess, that would correspond to, let me just be clear about this objective function. What I'm showing on this x-axis here is the value of just 1 pixel in the reconstructed image. So obviously this is a very high dimensional vector space in reality. We've got tens of thousands of pixels or voxels, but I'm just showing one of them here. And I'm showing the value of the least squares objective function as I change the value in a pixel. And what I'm saying here is that given some initial estimate or a guess of what the image is, so I'm showing that here. So I'm guessing a pixel value here. What I can do is find the gradient of that objective function. So this is a quadratic, it's parabolic. And so here the gradient, here the function is decreasing, the function is increasing. So here the gradient is negative, here the gradient is positive. And we can see that for a given pixel value, we can find the value of the gradient, and here it's negative. And then what we can see is that if we're here, we need to get closer to the minimum of that objective function by increasing the value. So if the gradient here is negative, then we need to subtract off a negative gradient in order to get a larger value of x, which will draw it closer towards the minimum of the least squares objective function. So that's the basic approach with these iterative algorithms, is to say, well, just given a candidate current guess of the image, take the gradient of the objective function in order to get a search direction, which I'm denoting with this red arrow here, which will get us closer to where we want to be, which is the minimum of the objective. Okay, so let's go through that in a little bit more detail then. Here again is the least squares objective function. And what we're saying is find the x, which when you plug it into the system model, will minimize that difference. Okay, and here I've just written out AX, matrix vector multiplication, in explicit subscript notation. So that's just very standard, hopefully obvious to you. And what we want to do then is find the gradient of that objective function with respect to a single pixel value. So remember, it's a high dimensional vector. So I'm just going to do a partial derivative with respect to a single pixel value xj. So what happens then is we'll take the derivative of this, partial derivative. The 2 comes down the front, cancels that half, which was a spillover from the Gaussian log likelihood, if you remember that. So the 2 comes down the front, and we just multiply by the derivative of this with respect to a pixel value xj. So in this summation, one of these will have an index xj, where b is lowercase j, and the coefficient of that is aij. We've got a negative there, so therefore the derivative of that with respect to xj is just minus aij. So that's a very simple calculation of the derivative, partial derivative. And then as we know, to get closer, I'm just going to spell out what that gradient is first of all. Okay, what we're going to do is evaluate that gradient for a particular fixed image estimate now. So the big subtlety here, but very important. Here, this is fully general for any x. Now I'm plugging in a particular estimate of the image reconstruction. I'm calling that superscript k to denote it's an estimate. So I've just put a k there, and I've just rearranged this. I've put the minus. The minus is just cancelled out there, and I've just put the aij in the front. And what I want to show you here is how simple that expression is. This sigma I over aij is none other than the adjoint of the system model, or the transpose. And then this, of course, is just ax minus m. So the gradient image for least squares is this extremely simple thing, which is to say, take your current image estimate, xk, forward project it with a, take the difference with your measured data, back project it, and that is the gradient of the least squares objective function. So very simple, intuitive calculation for the gradient. Now, having evaluated the gradient, we know what we need to do to get closer to the minimum. We've got to subtract that gradient off. So there we go, subtract the gradient at xk in order to get to a next better estimate, xk plus 1, which will be closer to the minimum of that least squares objective function. So there it is there. And I've just said, well, there's some step size that we need to take of that gradient image. The gradient image is just a difference of back projections. And then we subtract that off to get a better estimate of the reconstructed image. Okay, so that's just repeating what I've shown before. Next update is previous update minus some step size of that difference of back projected images. I find it much easier to look at it in vector form. It's so easy. Take your current estimate, forward project, difference, back project, some step size, and then you subtract that from your current image. Very intuitive. Okay, a quick aside here is that if you are in the unusually fortunate position of having a system model which is unitary or orthogonal, I say unitary to account for the MR case where you could have a complex valued system model. If it's unitary, that would mean that A star, or if it's orthogonal, that would mean A transpose, is equal to the inverse. If that's the case, then we can see that this least squares update for a step size of 1 automatically gives us the one-stop solution. Xk plus 1 is xk minus A star, A, xk minus m, A star A, if A star is the inverse, that's just the identity. And you're just left with, therefore, A star M. And all that's saying is, for example, if you had fully sampled k-space data for MR, this would say, take the conjugate transpose of your discrete Fourier transform, in other words, take the inverse Fourier transform of your measured data to get your reconstructed image in one go. So that's just an aside for the very bespoke and not very common case of fully sampled k-space data in MR. But just to emphasize, the reason things are not as trivial as that is because our system matrix is not unitary or it's not orthogonal. And so we do need to do a bit more hard work than just this direct inverse. Okay, so this is what it would look like in general for MR, for example, if we're just trying to go about minimizing this least squares objective function. I've just shown you that it's just given by this gradient-based update, and this is called gradient descent. And so we've got some initial image, we plug it into the gradient descent update, which if you remember is forward project, AXK, that's the forward project, difference, that's the prediction minus the measured data, back project, that's the adjoint or the conjugate transpose of the system model. And then you just subtract that from your image to get the next update. So very elementary algorithm. And of course, if the system model is not unitary, if it's undersampled k-space data, then in general here you'd actually get aliasing artifacts, some kind of wraparound effects due to the undersampling. Okay, so now I just want to quickly look into, notice that the big unknown in this, okay, was, well, the step size. What on earth do we use? How much step size do we use? Now, for all you deep learning fans out there, this is also known as the learning rate in terms of, this would be like batch gradient descent. And in deep learning, we often just use tiny learning rates and get away with that. But we want to be a bit more efficient than that when we're dealing with these simple linear models for image reconstruction. And so what I'm going to cover next is the case of steepest descent. So in other words, to try and optimize that choice of step size lambda. Okay, so just a reminder then, what is the gradient of the least squares objective? Well, we remember already, it's just this. Okay, back project the difference between your forward model and the measurement. And if I just expand that out, that's saying take your current guess of the image reconstruction, xk, forward project it, back project it. And if you like, that's like a back projected image in the context of PET, but you can still call it the same thing, I guess, for MR. You do your MR forward model, then the conjugate transpose here. And you compare that predicted back projected image to the measured data, which has been back projected, okay? And so this can be more compactly written as follows. In other words, just run X through this large square matrix A, which, if you like, is modeling the back projection process in one go, and compare it to the back projected data G. That's the gradient, okay? And in what follows in the quick slides is that I'll be expressing that gradient as just a gamma gradient vector for a particular estimate xk by using k, but for notational convenience, I'm going to be using the transpose. I may also use subscript k, but if you note, that's still a vector, so forgive the interchangeability of notation there. So yeah, gradient is just the difference between back projected images. Right, so we're trying to now optimize how much of this gradient image to add on to our current image estimate in order to get a better one that is closer to the minimum of the objective function. Now, of course, the objective function is not always beautifully set out. And so even if we optimize this search direction, it won't directly minimize the objective function. I'll show you a demonstration in a moment, just an illustration of that. First of all, then, just to go for the 2 pixel case here. So imagine I've got pixel value x1, pixel value x2, got some initial estimate, vector x superscript 0. So that would just be a value of 0 and 0 at the origin here. And we evaluate the gradient, which would be basically another image. And it's basically, therefore, defining a direction to go in order to minimize this least squares objective function. So I'm just writing that generally as follows. Next update is given by previous update. And in general, I'm going to say plus some scalar step size of the gradient evaluated at the current estimate. So here, at gamma 0 is the gradient evaluated at 0, 0 as the image. And what we're saying then is, as we know, the gradient is just the difference in back-projected images, or just given by that expression there. And we need to figure out how much of that to add on to get closer to the minimum, or in fact, to actually, more specifically for this search direction, to actually hit the minimum in that search direction. So I've got a bit too much text there. I'm just spelling it out, saying we need to progress along a step size alpha of that gradient direction for as long as that least squares objective function is decreasing to reach a new image x1. So here I'm just showing now, as we progress along there, I'm just showing the different gradients as we go down here to hit some minimum in that search direction. The search direction is just that gradient image, such that the gradient here at the new estimate needs to be orthogonal or perpendicular to the initial search direction. And that's how we know that we've minimized in that search direction. Okay, so the gradient at the new estimate x1 is just going to be exactly the same formula that we've been using all along. It's just that we're plugging in predictively x1 there to say that when it's put through h and compared to g, that's the gradient. And we're saying find the step size alpha that will minimize along that direction. And so the requirement is it's just an analytic calculation. You just require gamma 0 to be orthogonal to gamma 1. It all analytically drops out beautifully to tell you that the step size you need to take to get there in one go, the minimum in that search direction, is simply take the gradient image, forward project, back project, and then take the scalar product with the original gradient image. And then in the numerator, it's just the gradient image scalar product with the gradient image. So that's the analytically calculated optimum, well, optimum's a loaded word, but best step size we could take to minimize the objective in that search direction. So to give you the graphics for that, this is based on Wikimedia. And so here I've just got x0, an initial estimate, and I've got gamma 0 being my gradient search direction, and I want to get to some minimum at the update x1. I'm saying x1 is just the original estimate plus the step size times the gradient. Okay, and I'm just showing again that in one go, what we're doing is just keep going until the gradient at the new position is orthogonal to the original gradient. If you do the analytic calculation, it's what I just talked you through just now, and that is the steepest ascent algorithm. Now, what you'll notice is, I mean, that intuitively sounds like a great approach, but look at the graphic here. If we start here and we go in that direction, we arrive here. Then we go in the gradient in that direction, we arrive there, then there, then there, then there. The whole thing zigzags towards the least squares solution. So it's not a very optimal approach, which is why you may have heard of the conjugate gradient algorithm, which is a nice upgrade on steepest descent. So this is the conjugate gradient method. Again, we start off at x0, and we start off with the same search direction, which is the gradient image evaluated at the current estimate. And we go in the search direction, which I'm calling D0, which is the same as the gradient, to arrive just like the steepest descent algorithm at position x1. And now when we're at x1, this is where conjugate gradient changes. Instead of doing the naive steepest descent by adding on the gradient at that position, what we do instead is add on this hybrid search direction D, okay? So the search direction D is equal to the gradient at that position. That is a good direction to take, but it's going to zigzag if we keep only using that. So what we do is we take the gradient at the new position and we add on some scalar amount of the previous search direction. So what this calculates here is, you can see D1 beautifully for the 2 pixel case takes us directly to the least squares estimate by using a search direction D1 that's equal to D0 plus gamma 1, or rather I should say the search direction is gamma 1 plus some amount of the original or the previous search direction. And if you go through the mathematics, I've got a full derivation. In fact, I've got a video on this if you want to go into the details of it. What drops out are these two step sizes, or rather, sorry, the step size is alpha, and beta is the amount of the previous search direction that you need to use to add on to the gradient to get this hybrid, super efficient search direction D1, which, as I say, for the 2-pixel case, for the least squares objective, delivers you the least squares estimate in just 2 steps. Very elegant and avoids that zigzag of the steepest descent method. Okay, so that's enough on least squares for the moment. I now want to quickly move on to Poisson noise, which is the case for PET data. So you remember we did the Gaussian log likelihood in the earlier slide, relating that to least squares. Well, with Poisson noise, we deal with the Poisson likelihood. So instead of the Gaussian, I've got the Poisson noise distribution here. Model of the mean is given by AX, a particular element I of that forward model. So this is just the definition of the Poisson probability distribution. And then, as we saw before, we take the product of all of those probability distributions in order to define the likelihood of a particular image X. So this is like a continuous dependence on a vector X, given a fixed measured data M. Okay, we want to maximize the product of all of those probabilities. So manipulate X to maximize that probability for each and every sinogram bin in the context of PET data. As before, we take the logarithm to turn the product now into a summation and eliminate that horrible exponential term. And we end up with this expression here. So what you need to realize is, just like hopefully least squares is like a very obvious distance measure for you, the analogy in the Poisson case is always going to be this basic form, which is measured data log model minus the model. So just like you know that it's measured data minus model L2 norm for least squares, so you should also know, hopefully, sooner or later, that for the Poisson case, it's always of this form. And this relates to the Kolbach-Leibler divergence, which is a way of expressing it as a kind of asymmetric distance measure. But for the moment, we're just going to focus on the classic case of maximizing this Poisson log likelihood. But first of all, I'm saying, unlike the Gaussian case, remember the Gaussian case, we could solve, even though we didn't, we had to do it iteratively, but in principle, you could solve it directly. This, you can't solve directly. So you're already forced into iterative methods. And so what we're looking for then is an algorithm that will find an image X, which when forward modeled, and you take the logarithm, multiply it by the measured data and subtract off the model, that will give a maximum of this Poisson log likelihood. And that's equivalent, of course, to minimizing the negative of the Poisson log likelihood. And I guess in optimization, we often like to minimize things. So you'll have to start talking about the negative Poisson log likelihood if you want to put it in a minimization context. So let's quickly talk you through an algorithm that does that. That's pretty much bread and butter for radionuclide imaging, PET and SPECT, which is the following. So here's our, I've rather crudely represented it as this nice sort of parabolic function, but it won't necessarily look like that. This is the Poisson log likelihood. And we want to find the X that maximizes that. So here is the gradient of the Poisson log likelihood, just very crudely shown as this linear line here. And now, because I want to maximize the function, if we've got some estimate xk, then to get it closer to the maximum of the Poisson log likelihood, we're going to need to add on the gradient. Okay, so first of all, let's find the gradient. And for that, just a reminder of what the forward model is. That's what I showed on the very early slides. Forward model is just a matrix vector multiplication. So let's take the gradient, the partial derivative of the Poisson log likelihood with respect to a pixel value. So this is a very simple bit of mathematics. It's just the logarithm of the model. So that's just 1 over the model multiplied obviously by m and multiplied by the derivative of ax subscript I. So we just take the derivative of that with respect to a pixel xj, and that's going to be aij. So that's why that appears there. And the same argument holds for the derivative of that. So it's just sigma aij. And this then is the gradient of the Poisson log likelihood. And again, we can consider that as an image, okay? It's a gradient image. So remember, for the least squares, the gradient of the least squares objective function was just a difference of back projected images. And so likewise, for the Poisson log likelihood, the gradient image can also be understood in a very intuitive way, which is take your image, forward project it, take the ratio between the measured data and the forward projection, back project that ratio, and then subtract off a back projection of unit data. This is also known as the sensitivity image. So remember, to get closer to the maximum, now we're going to need to add on the gradient, because here the gradient is positive, and that's the direction we need to go in if we're below, if our value is too small compared to the maximum likelihood estimate. So that's what I'm showing here. Next estimate is previous estimate plus the gradient image, okay, which is just this expression here. I've just plugged that in there. And now the fudge, which I won't motivate here, is to say that for the core algorithm used in PET imaging, we use a particular modification of that gradient direction. What we do is we take the image value and divide by the sensitivity. So the image divided by the sensitivity image. And that's like it's not really a step size, because this actually varies across the image. But it's just like a multiplicative modification of the gradient of the Poisson log likelihood. The reason for doing this, well, an intuitive motivation, is that you can see that by multiplying it by this, that term will cancel with that term there to just leave us a minus x here, which will cancel that one there, which means we end up with a purely multiplicative algorithm. Very simple to implement. So I'll talk you through that in this slide. You'd have an initial image, and then you do an EM update, and the EM update is just a forward projection, a ratio of the measured data to the forward projection, back projection, and then effectively a multiplication. You've got to normalize by the sensitivity image. And that's all you do to get a sequence of estimates. I've just unrolled them, kind of deep learning style here, as a series of EM updates. Okay, quickly now, I think we started about 15:15 or so I'll just take 5 minutes, hopefully. Regularization, noise is a problem in PET, and incomplete data is a problem for MR and CT, because we've got undersampled MR, missing angles in CT. So how are we going to deal with that? Well, first of all, just to spell out the problem with PET, if we've got high count data, we get nice images, low count data, poor images. So noise is a problem, and we need to regularize to compensate for noise. With MR, the problem is often undersampling. So I'm just showing a very simple example of stripping out some of the K-space lines here. And that results in the aliasing kind of wraparound artifacts that you're probably familiar with already. And again, need to regularize, but this time for a different reason. And CT, there'd be a similar case where you have missing angles giving artifacts in the image. So the way to deal with that statistically is to take your likelihood function. Remember, the least squares case was just the Gaussian log likelihood. Poisson case was also built into likelihood. Just multiply your likelihood function by a probability of a particular image X. And we're going to define how probable an image is based on some energy measure U. And so what we're going to do is define it as follows, because remember, we're going to take the log, like we took the log of the likelihood, we're going to take the log of what's called the posterior, which is the prior probability multiplied by the likelihood. So that's why we're defining it like this, knowing we're going to take the logarithm and just be left with this term here, which is basically like a penalty for the data fidelity. Okay, likelihood is data fidelity, and our prior is here. So when we take the log of that and that's what we'll be doing, log posterior maximization. We can then view that as a penalty function. And I realize I'm very low on time here, so I'm just going to quickly show you examples of the energy function U that we can build in here to modify our likelihood. So here's a quick example then. Imagine that's an image X, PET image. What we could do is zoom in and say, well, look, there's one pixel value xj. And we'll define our energy to be simply equal to all of the pixel values added together. But we've got to account for positives and negatives in general. So what we'll do is we'll take, for example, the square of that, which would be like a quadratic, so-called Tikhonov regularization prior. And when we get to the case of the difference, it would be an absolute value here used for a difference of pixel values, which would be total variation. So let me just build that in. So first of all, just focus on that one as just the Tikhonov case, just square all the pixels. The idea being that if you've got a very noisy image, you'll have very blown up values in the image, which give a large energy measure, and that would be a penalty for the data fidelity for the least squares objective function. But to be more elegant, we can look at pixel pairings, xc, xj. and just look at the difference between them. Again, we could square that for a Tikhonov style regularizer, or we could take the absolute value instead, and that would be now total variation, and then we sum that all up within a neighborhood. And then, of course, we could also account for the fact that distances between pixels mean that if these pixel values are different, then we can allow that to be the case if they're far apart. So it's like a permission to be different if you're far apart. Okay, so really out of time. So for PET, we can go through this more in the PET session. One algorithm would be as follows, where you basically do a data fidelity based update, then you do a denoising update, fuse them together and keep iterating. So there's the map objective function. Notice this is the Poisson log likelihood. And now I've got that exponential minus beta u, but with the logarithm, it's just minus beta u. So that's a penalty for the Poisson likelihood. Here I've got an example quadratic. So this would be like a Tikhonov regularization with a finite difference operator here. So it's just difference in pixel values with a weighting factor that could be guided by MR information. We'll be doing that next week. And the algorithm that will be dropping out will be just that EM algorithm I've talked you through already, forward project ratio, back project multiply. And here we'd have an update based on the prior, and effectively it's just a denoising smoothing operation, and we just join them together. So the update here is just a fusing of the data fidelity update with the regularization prior update. And so this is basically the method of De Piero from way back in, I think, 1995. Okay, really short on time. Chris, please step in if I'm going too far. Just take a couple more moments. For MR, we've got gradient descent, and there's the least squares objective function, and we could just penalize it using, for example, some transform operating on an image X, and then some potential function. I'll give you a concrete example to make this clearer. So Tikhonov regularization would be least squares difference, and then penalizing this data fidelity term with this regularized penalty here, which is what we're saying here is take the image X. You could just use an identity mapping for vanilla Tikhonov and just penalize any image that has large values, or you could do the finite differences, looking at the neighborhoods. That's what I showed you earlier in that graphical example. And this could actually be solved directly with the conjugate gradient algorithm. You can do more elegant things than that. You could get into, instead of doing L2 norms, you could do L1, and that's just taking the sum of the absolute values, where what you could say is, well, I want to find some transform W operating on X such that this only has small values. So imagine what you could do here is, for example, finite differences, just look at neighborhood values, just taking the gradient, take the absolute value, that'd be total variation. And that would encourage images that are sparse in terms of gradients, okay? Because the L1 norm would just sum up all those values. And if the gradient, if the image is flat in various regions, that would pass through with no penalty. But you could use a wavelet transform, and I've just shown you that graphically here. These are coefficients for the wavelet transform of this image, and we could just demand that there be few coefficients used to represent the image X. So these all need whole 1 hour lectures in and of themselves. I'm just covering basics here. And this is what we do with deep learning, but I'm really out of time. So I think I won't have time to cover this, and I'll pass back to Chris, who now has 3 minutes to cover his half-hour talk.